Today, so if you don't know me, I'm Clayton, and it's a pleasure to have Daan Adcock today, and he's from the Department of Math at Simon Fraser, and he's going to talk to us about polynomial approximation of high-dimensional functions from irregular to regular domains, and I'm sure he'll tell us how that relates to UQ in a minute.
I hope to, yes. Thank you. So first of all, thanks to the organizers for the invitation. It's very nice to spend some time here visiting the program. So I think I should first say that I'm an applied mathematician, so this is going to be an applied mathematics talk. And I think the second thing I should say is that I am a bit of an outlier to the UQ community. It's a fairly recent area for me, so I've learned a lot while I've been here. And with that in mind, this is going to be an approximation talk. It's going to be about high-dimensional approximation. So as you can probably tell from the title, the topic of this talk is polynomial approximation. Of course, we've seen a lot of polynomial approximation already this week. It's, of course, one of the very, very common tools in UQ and various other areas. But what I want to focus on is an issue that is perhaps not discussed very much, which is irregular domains. So most commonly, we construct polynomial approximations in tensor product domains, so hypercubes. And really the goal of this talk is to try and understand how much of the nice properties of polynomials we can extend to more general domains. So, roughly speaking, this talk's going to be in two components. The first part of the talk, I'm going to give you an overview of some of the work on polynomial approximation in high dimensions that's happened over the last 5 to 10 years, a little bit of which you've already heard in talks this week. And then the second half of the talk is going to be about extending this to irregular domains. I should probably say before I begin, or I should definitely say before I begin, this is mainly joint work with Daan Huybrechs, who's been my long-term collaborator. In fact, I first met him at the Isaac Newton Institute about 12 years ago, so it's very nice to come here and present some joint work. And I'm also going to talk about work with a few other people, so my former student, Anyi Bao, who's now at UBC, my postdoc, Simone Brugia-Paglia, and also Clayton as well, because everyone knows. Okay, so let's dive straight in. So, this talk is about polynomials, and orthogonal polynomials in particular. So why do we like orthogonal polynomials? Well, they are great ways of approximating smooth functions on simple domains. And by simple, I mean intervals in 1D or hyperrectangles in multi-D. And as far as I'm concerned, there are 4 reasons why we like polynomials so much, or 4 reasons that are going to be relevant for this talk. There may be other reasons, but I won't discuss them. First of all, simplicity. Multivariate polynomials are just tensor products of 1D orthogonal polynomials. Secondly, accuracy. We understand we have plenty of theorems about convergence rates of polynomial expansions in terms of smoothness and smoothness classes. So you saw in Chris Schwab's talk on Monday this idea of holomorphy, and with that you get estimates on the rate of convergence of polynomial approximations. Thirdly, a third point which is very important and will be very important for this talk, but is perhaps not discussed so frequently, is what I'll say stability. If I expand a function, f of x, in orthogonal polynomials or orthonormal polynomials, then the norm of its coefficient, x, is equal to the norm of the function. So this means that I cannot have large coefficients when my function itself is not large. So I cannot have things like cancellation errors, etc., etc. Okay. So this will be a very important point for later on in the talk. Finally, we know how to compute polynomial expansions. Okay, we have different schemes, interpolation schemes if we can find good nodes, discrete least squares, and then more exotic things such as compressed sensing, which is an area I've done a lot of work in and which is an area I'll touch upon in a few minutes. Okay, so this talk, what is this talk about? This talk is primarily motivated by the problem of saying, suppose now my domain is not a hyperrectangle, but I still want to compute a polynomial approximation. What can I do? And of course, there are all sorts of issues that we might have to face. We could have non-smooth boundaries, we could have unknown boundaries, or boundaries that are difficult to parametrize. We could have holes, we could have non-simply connected domains. etc., etc., etc. Well, what would we like? What would be the holy grail of multivariate polynomial approximation on irregular domains? Well, basically we'd like all the nice properties that we have for tensor product domains. So, first of all, we'd like something that is simple. Okay? In particular, we'd like an approximation scheme that works for general domains in any dimension, does not require parametrization or even knowledge of the boundary of the domain. Okay? We don't want to have to get into the business of trying to describe our domain in order to construct our approximation, or describe it in any detailed way. Secondly, we want accuracy. We'd like convergence rates that depend on smoothness in exactly the same way we have in tensor product domains. And we want stability. Okay? So I'm going to be a bad numerical analyst and mix stability and conditioning in this talk, but we'd like a mapping from our samples to our approximation that is well conditioned. And secondly, we'd like the norm of the coefficients of our approximation to be approximately the norm of the function, exactly like we have in tensor product domains with Parseval's identity. Finally, we want efficiency. So in efficiency in this talk, I'm not going to refer to computational efficiency. I'm going to talk about the number of samples we need. Okay, so the sample complexity, in other words. So if I'm going to sample my function and I want to reconstruct my polynomial approximation, I'd like to be able to show that the number of samples I need, chosen according to some strategy, should scale mildly with the degree of the polynomial I'm using, and ideally independently of dimension, okay, or as independent of dimension as I could make it. Okay, so we want to, as much as possible, try and avoid the curse of dimensionality. Okay, so why am I interested in this? There are many problems where the domain turns out to not be regular. Okay. So one of them is, for instance, surrogate model construction in UQ. Of course, you're all the experts in this business. I am not. So I have to be very careful what I say here. But after speaking with a number of people, especially these people at Sandia, it was pointed out to me that if you're trying to construct a surrogate model, you may be in a situation where your forwards model, which may be some black box, is not well defined in some regions of parameter space. So you assume some tensor product domain, you generate samples in that domain, that's randomly, you run you compute your forward model, and it gives you some kind of failed evaluation. So maybe it gives you a non-physical quantity, maybe a negative density or whatever, or something like that. So in that case, you are essentially working on a non-tensor product domain. You're working on an irregular domain at that point. So what I've included here is a picture taken from this paper where they are looking at this climate land model, which is admittedly something I know nothing about, but the point is that when they do this, they sample uniformly on a on a cube, and roughly about 20% of their evaluations fail because the domain of the function that they're trying to approximate is actually irregular. Okay, so and then there's the issue as well. Forward model might be discontinuous. Again, if you have discontinuities, then effectively you're separating your function into two or more smooth regions. Okay, so which will generally be irregular. So that's the first application. Second application, so another set of related techniques in UQ. So we saw a nice talk by Ralph Smith on Monday on active subspace techniques. So what do I do in an active subspace technique? I have a high dimensional function. I try and learn its important directions, and then I project down to a lower dimensional space. And if my function is defined on RD, everything is fine. I project down to a lower dimensional function defined on K, for example, where K is less than D. However, if your function happens to be defined on the unit cube, and you do this projection down, then the domain of the projected function is not a tensor product domain. It's this type of polyhedral domain or polytopic domain here, which is called a zonotope. Okay? And these can be very complicated domains. Okay? So naturally, if you do any kind of active subspace type technique, you will end up at the end of the day with an approximation problem in several variables that is defined on a domain that's not tensor product type. Finally, just going back to a few sort of more classical numerical analysis topics. If we want to solve numerical PDEs in 2 or 3 dimensions, suppose we want to get a meshless solver, completely meshless solver that's spectrally accurate. Well, it's not clear how to do that. And it's not clear how to do that without being able to very carefully parametrize the boundary of your domain in particular. And then, for instance, if you're interested in numerical computing with functions, things like Chebfun, the question of how do you extend things like Chebfun to irregular domains in 2 or more dimensions is completely open. All right. So, with that in mind, I'd like to spend the next bit of the talk talking a little bit about polynomial approximation in tensor product domains, to give you an idea of the flavor of what we know in tensor product domains, and then we'll try and see if we can extend this to irregular domains. So, first of all, a little bit of notation. So, throughout the remainder of the talk, D is going to be the unit hypercube. I'm going to be working on compact domains, so we'll just normalize it to be the unit hypercube. For now, we're going to let nu be a tensor product probability measure on D, and we'll let phi n be an orthonormal polynomial basis of L2 nu D. And then our function f can be expanded, of course, in this orthonormal basis with its coefficients x, n, just given as the inner product. Okay, so all very standard. So, what does polynomial approximation look like in multiple dimensions? Well, as Chris Schwab was saying in his talk on Monday, the polynomial approximation in high dimensions is really a question of best n-term approximation. So what would we like to do? We'd like to approximate our function f by the largest n expansion coefficients in absolute value. So we have this infinite expansion here. We pick the largest n coefficients in absolute value, the largest capital N coefficients, and that forms our approximation to f. And this would be referred to as the best n-term approximation of f in the polynomial basis. Why do this? Why consider this? Well, as was explained in detail earlier in the week, the reason we do this is because we have very good estimates for the rate of convergence of the best n-term approximation. Specifically, if you consider these model parametric PDEs, these elliptic diffusion problems, etc., then you can say that the rate of the best n-term approximation, the error goes down something like n to the 1 minus 1 over p, where p is a number between 0 and 1, depending on the PDE, depending on the diffusion coefficient. So I'm not going to go into any of the detail about the theory of this. There's been a huge amount of work proving these kind of estimates for different types of PDEs. Yes?
Okay, so the phi's are orthonormal, and the best approximation is you just order the coefficient.
Yep.
Is that right?
Yep.
Okay, thank you.
And so the point here is that this rate is independent of the dimension. Okay, under the right conditions on your PDE, you can say that you formally have a rate that's completely independent of the dimension of your problem. Okay, so best n-term approximation is fine, but we'd like to have a little bit more structure, or a little bit more of a structured approximation. And to incorporate this, one can introduce this notion of lower sets, which is something we've seen already in a few talks this week so far. So what is a lower set? A set of multi-indices lambda is lower if whenever I have an n that's in lambda and I have an n primed, which is component-wise less than or equal to the entries of n, then I also have the n primers in lambda. Okay. These are also called downward closed or monotone sets. Okay. And somehow these are very natural objects for polynomial approximation. If I have a multi-index space of 2 indices, so if I have an index out here that's in my lower set, that's saying that all these indices in the rectangle below it should be in the lower set, which is very natural when you think about polynomial coefficients. In most smooth functions, you're not going to have a large coefficient here without the coefficients here also being large. So what can you say? Well, with the same theoretical setup and looking at the same types of model problems, you can say that not only can you achieve a rate of n to the 1 minus 1 over p for the best n-term approximation, but you can actually achieve the same rate with a sequence of lower sets. So you can find a sequence of nested lower sets of cardinality n that give you the same rate. So you get a quasi-optimal n-term or quasi-best n-term approximation by working through lower sets. Excuse me. So we know a lot about best n-term approximation with polynomials in tensor product domains. How do we actually compute this approximation, or compute something close to it? Well, there are sort of there are three schools of thought on this. One school of thought is interpolation. I'm not going to talk about interpolation at all. But what I am going to talk about is discrete least squares, and then I'll say a little bit about compressed sensing as well. So let's suppose that I have a target multi-index set lambda, which is where I think my coefficients are going to be. So this could be a lower set. Actually, let's assume it's a lower set from now on. Let's construct P lambda to be the finite polynomial space corresponding to the polynomials with indices in lambda. And then what do? Well, we take samples of our function, and I'm going to do a very simple sampling, just Monte Carlo sampling according to the measure nu. I'm going to take m of these samples, where m is bigger than n, and then I'm just going to compute the least squares fit in this polynomial space. So I'm going to take a very simple sampling here. I'm not going to talk about more sophisticated samplings. There are more sophisticated things people can do, but this is going to allow me to prove theorems for the moment, and I'm not going to try and get into the business for the moment of coming up with more improved samplings. There is work in this direction, but I'm not going to touch on that at all. Yes?
Just to understand, so the polynomial space, you fix it a priori, you give it as given, or?
For the moment, yeah, for the moment. Okay, so that's actually, you're anticipating what I'm going to say in a couple of minutes' time. So if I suppose, as you say, suppose I know the lambda, so I construct my polynomial space, I solve my least squares problem, then the question that we're interested in now is how big does m need to be, okay, in order to make this approximation quasi-optimal. And again, there's a bunch of theoretical work on this, including by Fabio, who's done a lot of work in this direction, and his students and postdocs. And a typical result is of the following form. So without going into really any of the details, discrete least squares is well conditioned and quasi-optimal with high probability, provided the number of measurements m scales like this. So the key thing here is this constant. So this is what I'm going to refer to as the constant of the Nikolsky inequality for the polynomial space P lambda. And then I have this log factor as well. Okay. So just to be clear, what do I mean by the constant, the Nikolsky inequality? The Nikolsky inequality is this inequality here. And what it says is it says how large can a polynomial grow uniformly on my domain if it's in comparison to its L2 norm. Okay. So this is a certain number. And it's characterized by the polynomial by the polynomials, the measure nu, and the index set lambda. So this just reduces sample complexity to a classical question approximation theory, estimating the constant of Nikolsky's inequality, and you can do this for different measures of interest. And if you go through this analysis, for instance, if you work with the uniform measure on your cube, then the constant is n squared. Actually, there's a typo here. I think this should be the Nikolsky constant squared, just to be precise. And if you use the Chebyshev measure, then the constant is n to the log 3 divided by log 2. Okay. And so the nice point here is that you're independent of the dimension. Okay. You don't see the dimension d in these estimates. Okay, so that's least squares, and that's a summary of sort of what a lot of work in least squares that's gone on in the past 5 or 10 years in estimating these sample complexities.
So just another choice.
Yep.
So the Chebyshev measure is the arc sign.
Arc sign measure,
You
yeah.
take the product
Mm-hmm.
of that in different dimensions, do you?
Yeah, exactly. Yeah, yeah. Okay, so what's the problem with least squares? Well, the problem with least squares, as was already alluded to, is that this target lower set lambda is typically not known in advance. Right? So we know that we can get a quasi-best n-term approximation in lower sets, but we don't know exactly which lower sets to use. So one can try and identify these lower sets in an adaptive way. But what I'm going to do instead is do something completely different, and that's use the ideas of compressed sensing. Yeah. And I'm going to try and summarize this in 2 slides without going into too much detail. So, we don't know the target set lambda where we think the target lower set lambda where we think our coefficients are going to live. But we do know something. We know that the union of all lower sets of a given cardinality n is a finite set, and it's actually precisely the hyperbolic cross. So what can we do? We can set up an underdetermined system of equations. So a big fat matrix corresponding to our interpolation problem based on this hyperbolic cross. That becomes our search space of multi-indices. And then we try and put a regularizer on that. That promotes the lower set structure that we want to get. And it turns out, through a lot of analysis, you can discover that a good regularizer to use in this case is weighted L1 minimization with a very specific choice of weights. And this was already talked about by Huang Tran in his talk a couple of days ago, so I'm not going to go into too much of the details about this. But the point is that if you put the right regularizer on with compressed sensing, you can recover a quasi-optimal approximation without having to know the lower set where your large coefficients live. Yeah. I should note here that the use of weights is very crucial. If you solve the unweighted L1 minimization problem, you end up with sample complexity estimates that can potentially be exponentially large in the dimension. Okay, so to summarize a bunch of work, and without going into too much of the details, because the details are relatively lengthy to state, I just want to say what the sample complexity is. So if you use compressed sensing techniques with weighted L1 minimization to compute a polynomial approximation, the number of measurements you need, or the number of samples you need taken from the measure nu, are scales like this. Okay. So it's very similar to the least squares case. The only thing now is we have to take the maximum of the Nikolsky constant over all possible lower sets of cardinality n. Okay. And we pay a little bit more in the log factor here. In particular, we pay a small log factor in the dimension as well. Okay. The point, though, is that this factor is the same as the discrete least squares factor. Okay, so the only difference is in the log factor. In particular, if we sample from the uniform measure, the sample complexity is n squared. If we sample from the Chebyshev measure, it's n to the log 3 over log 2. But the point is we don't need to set or have any knowledge of our target set lambda in advance. Okay, so to summarize, in tensor product domains, multivariate polynomial approximation in tensor product domains is increasingly well understood. We know a lot about approximation rates, and we know a lot about how to compute quasi-optimal polynomial approximations. There are lots of further topics, none of which I'm going to touch upon here, but suffice to say there's much more that can be said on this, but our knowledge of this area is becoming increasingly mature. So I'd like to now move on to irregular domains, which is going to be the topic of the rest of the talk. But before I do, are there any questions about what I've said so far?
It's just it's very strange. Log 2 upon log 3 is the fractal dimension of the Cantor set. Is there any connection?
Oh, that's a very good question. Off the top of my head, not one that I can immediately see, but there may well be. So I would have to think about it. It's a good question, though. Okay, so let me move on to regular domains now. So, suppose now we have a function f that's smooth, but it's defined on a domain omega that's not a tensor product domain. How are we going to we want to do a polynomial approximation. So how are we going to do this? Well, I'm going to propose something that's incredibly simple, which is the following. So, first thing to do, and really the only thing that is particularly difficult, well actually no, none of this is particularly difficult. We're going to pick, so our domain of our function now is going to be omega, and the first thing we have to do is pick a tensor product domain that contains omega. Okay. So this could be a hyperrectangle, it could be a torus, maybe we want to do Fourier approximation, or it could be the whole of Rd. Then, We're going to pick an orthonormal polynomial basis on D. So Legendre polynomials, the Fourier basis, Hermite polynomials, your favorite orthonormal polynomial basis. Then we're going to pick m sample points according to some strategy in omega. Okay. So for example, they could be from the uniform measure on omega, if omega is compact. And finally, given the samples of f, we're just going to approximate it in our polynomials restricted to omega. Okay. How are we going to do this? Well, we could do least squares, we could potentially do interpolation, we could also potentially do some kind of compressed sensing technique. I'm going to keep things simple for the rest of the talk, and I'm going to talk about least squares only. When I say I'm going to keep things simple, that means that I actually do not know how to do interpolation or compressed sensing in irregular domains. Okay. So this is the technique. This is, in essence, all there is to it. The rest of the talk is going to be understanding about the stability, the accuracy, and the efficiency of this approximation. Okay, so I should point out that this is very simple, and therefore it's obviously been done before many times. This first came to my attention through sort of past work in the 1990s on sort of fictitious or embedded domain methods for PDEs. Then there was a bunch of work in the early 2000s and mid 2000s, some of which I was involved on as well, in looking at using the Fourier basis, computing what are called so-called Fourier extensions. So there's been a lot of work in this direction, but most of this is for low-dimensional problems, 1, 2, or 3-dimensional problems. I should point out that despite this Fourier extension name here, we don't care about what happens to our approximation outside of omega. We only care about the behavior in omega, how well we approximate our function in omega. The second thing I should point out is this is really inadvertently what people are doing in quite a lot, in many practical UQ simulations. If you're constructing a polynomial approximation of a forward model, and your evaluations that you're using come from some subset of the tensor product domain, then you're effectively just doing the approximation that I suggested. Okay. The key point is there's no theory to underlie why this works. Okay. So that's what I'm going to try and provide. All right, so first thing to point out. So if you recall, I mentioned this holy grail of multivariate approximation, and the first criterion should be simplicity. This is clearly an extremely simple thing to do. Okay, you're using simple tensor product basis functions. You're not trying to orthogonalize a basis on an irregular domain in d dimensions. That sounds hard to do. You don't need to parameterize the boundary or anything like that. You can have a completely general domain, all sorts of unpleasant features in your domain. And in fact, your domain doesn't even really need to be known. Okay? It's going to be implicitly defined by the data in some sense. So really your knowledge of the domain is minimal. Okay, so a little bit more setup. I'm going to specialize the setup even more now. This is not to say that we don't have results for more general cases, but to make the presentation just a little bit more succinct, I'm going to specialize to the following case. So for now, from the remainder of the talk, omega is going to be compact, and let's assume without loss of generality it's contained in the unit hypercube. I'm going to consider the Legendre basis on the unit hypercube. Lambda is going to be a subset of size n, exactly as we had before, that defines a polynomial space that's n-dimensional. Okay, and typically we'll think of this as being a lower set as before. Then our sample points, we're just going to do a simple sampling. We're going to draw them from the uniform measure on omega. Okay. And then we'll draw m samples where m is greater than or equal to n. We'll set up and solve our least squares problem. So from now on, A is going to be the matrix of the least squares problem, B is going to be the right-hand side. And then once we have the solution of the least squares problem, we'll compute our approximation f hat. Two index sets to keep in mind. I am going to talk about two index sets, so the total degree index set and the hyperbolic cross index set. These are mainly so I can say things about the approximation rate in what follows. Okay, so first thing I want to talk about is stability and accuracy of this approximation. And really up to this point, everything sort of seems fine. This is a very simple approximation. I mean, you set it up and solve. Everyone can do this. You just hit backslash in MATLAB. Okay? It doesn't seem like there's going to be any problem with any of this. However, there is. Okay? There is a potentially big problem. And the big problem is as follows. If I take an orthonormal basis on a domain D and I restrict it to a subdomain, it's no longer orthogonal. And in fact, it's no longer a basis. In fact, it's a redundant system of functions. Why is this? Well, take any function in L2 omega. Well, I can write it in infinitely many ways as an expansion in this system. Why can I do that? Well, take f, extend it in any way you like to D, compute the coefficients of that function with respect to the orthonormal polynomial basis on D, and then just restrict to omega. Okay. So this cannot be a basis. It's a highly redundant system of functions. And what does redundancy mean? What does redundancy mean for us as numerical analysts? Well, this means ill conditioning. Okay. So redundancy implies that when I truncate this system and I consider a finite set of polynomials, while these are technically linearly independent, because obviously n polynomials are linearly independent, unless I do something very silly, it is approximately linearly dependent for large n. And how approximately is it? Well, we can quantify this by looking at the gram matrix of this system. So the gram matrix is just the inner products of the basis functions over omega. And if we look at the condition number of that, that gives us a measure of how linearly dependent this system is, or how close to being linearly dependent. And you can relate the condition number to what's called the Ramez constant of the domain. So this is the second approximation theory inequality that we'll see in this talk. So what is the Ramez constant? The Ramez constant is the maximal growth of a polynomial from my polynomial space on D in relation to its maximal size on omega. So if I have a polynomial on omega, how large can it grow outside omega and within D? And it turns out the Ramez constants can grow extremely rapidly with n. So for example, if I take the one-dimensional case where D is negative 1, 1, omega is 0, 1, then the Ramez constant looks like 3 plus 2 root 2 to the n. Okay, so this is exponentially large. Yeah. So we are approximating a function using a finite system of functions that's nearly linearly dependent. This seems like an extremely bad idea. Okay? We're going to end up with a very ill-conditioned least squares problem to solve. We all know, we all teach our students that one shouldn't try. One shouldn't expect any accuracy. You're solving a very, very ill-conditioned problem. However, it turns out that something is going to save us. And what's going to save us is the fact that this system, while not a basis, does have a lot of structure. In fact, it's a frame of this Hilbert space. Okay. So what is a frame? A frame is a countable set of a Hilbert space. So frame H could just be an abstract Hilbert space here, and it's an abstract set that satisfies this property. So if I look at the L2 norm of the coefficients with respect to the frame, so just the inner product with respect to the frame elements, this should be equivalent up to constants A and B to the Hilbert space norm of any element F in the Hilbert space. So that's what an abstract frame is, and it turns out that restricting an orthonormal basis to a subdomain always gives you a frame. Okay, so I should point out frames are not something your average numerical analyst, and I assume also your average statistician has heard of either. But they are a huge topic in image and signal processing, encoding theory, sampling theory. They're used all over the place in that area of the sort of applied math / engineering communities. So, what does being a frame give us? Well, okay, so I've said that this gram matrix is extremely ill-conditioned. Okay. So one can then ask the question, well, what do its eigenvalues look like? And it turns out that if you have a frame and you truncate it, so you take n elements from the frame and you look at the gram matrix, it turns out that this will always be ill-conditioned, but the eigenvalues always look something like this. You always have a cluster of eigenvalues that are good, that are not close to zero, a narrow transition regime like this, and then you have a bunch of small eigenvalues clustering near zero. Okay. And it turns out the reason for this is because the Gram matrix is a finite section approximation to the infinite Gram operator of the frame. The Gram operator, its spectrum contains zero, and the rest of it lies between the frame bounds A and B. Okay, so you view this as a finite approximation to that singular operator. So what can we do? Well, let me say in a little bit more detail. For this polynomial frame, we have a nice interpretation of the eigenvalues of G. Or let's actually think about the singular values of the least squares matrix. Okay. So just to point out, I can transition between talking about singular values of the least squares matrix and eigenvalues of the Gram matrix, because in expectation, A star A is equal to G. Okay. So for this polynomial frame that we've been looking at, the small singular values correspond to polynomials which are small on omega but large on D. Okay. What does that mean? Well, that means that actually I don't need these in my approximation. Okay? I only care about approximation in omega. I might as well throw out the small singular values and the small singular vectors because they give rise to polynomials that aren't going to affect my approximation in any way. So what are we going to do? Rather than working with A, we're going to regularize, and we're going to take the singular value decomposition and just throw away all the singular values below some threshold epsilon. Okay. So that's our strategy. Now, and we know through this argument that this should not affect our approximation unduly, because we're throwing away polynomials that should not affect how well we can approximate our function. Okay, so here's the main result. Suppose now we have our least squares problem here, and we're going to compute the truncated SVD solution of this least squares problem. Let's call this x hat epsilon, and then we'll write our approximation as f hat as before. So, what can we say about this approximation? Well, first of all, here's a bound on the error. Okay, so here's a bound on the L2 norm error in terms of a constant c depending on m, lambda, and epsilon, and a factor e. And think of this as a best approximation term. This depends on lambda and epsilon and f, but is independent of m. It's independent of the number of samples. Okay, so I'll talk about this more in a second. Okay. So this is what the approximation error looks like. We can say something about the coefficients. They're bounded as well in terms of this approximation error. And finally, we can say something about the condition number of our approximation. So if we consider the mapping from our data that's contained in the vector b to our approximation f hat, we look at the condition number of that. That's again bounded by this constant here. So what does this mean? If I want to understand how well this approximation does and how stable it is, I need to do two things. First of all, I need to say something about this best approximation term here. And then second of all, I need to say something about this constant. Okay. So I'm going to deal with the best approximation first, and then we're going to estimate this constant. And it's going to be the same game as we saw in tensor product domains. We're going to need to have a condition on the number of samples we take m to ensure that this constant is order 1. So what can we say about the best approximation error? Well, here it is again. And this is perhaps a slightly odd thing. Okay, so it contains sort of a best approximation term. So it's an infimum over all polynomials of the L infinity norm of f minus p. So that's a best approximation term. If we just had that term, this would just be a classical best approximation thing. But we have this secondary term here, which is epsilon, where epsilon is our singular value threshold, times by the L2 norm of the polynomial p, but now over the whole extended domain d. Okay. So this is what I like to call the stable approximation property. This is asking the question, how well can your function be approximated by a polynomial p in p lambda on the domain omega, so that's the first term here, and subject to the condition that that p does not grow too large on the domain d. Okay. So that's where the stability comes in. So, what can we say about this? Well, in order to say sort of more concrete things about this, we'll need to say something about lambda. Okay, we'll need to specify our index set, and we'll need to specify some regularity of f as well. So I'm going to present two results. These are certainly not the only results one could present, but I want to present these two results to illustrate that we can get some concrete estimates. So first of all, suppose my function f is smooth in omega only, doesn't need to be defined outside omega. And suppose omega is Lipschitz, and let's suppose more precisely f has m orders of classical Sobolev regularity in omega, then this best approximation error looks like n to the d minus m plus epsilon, where n here is, I'm using a total degree index set, so little n is the degree of the total degree set. So what does this say? This says that this best approximation error is going to converge down at rate n to the d minus n until it gets to epsilon, and then it'll just level off. So the smoother your function is, the faster that initial convergence is going to be, and then you'll get to roughly level epsilon, and then you'll stop. So in practice, obviously, we can choose epsilon, so we set it according to the desired accuracy that we'd like in our approximation. So that's the first case. But of course, this doesn't scale very well in high dimensions because you're using a total degree index set. We know that grows very large. So the question is, what can we say about a hyperbolic cross index set? Well, here what are we going to do? We're going to assume that f is in the mixed Sobolev space of order m, and then we can prove the following estimate. We can show that the best approximation error is bounded by n to the 1 minus m times by the Sobolev norm plus epsilon times by the L2 norm of f on d. Okay. The key point here is we're assuming that f is in this Sobolev space, but now this is defined on d as well. So we're assuming that f is actually a smooth function over the whole of d. And then we can get this kind of rate here. This holds for the hyperbolic cross, so we can say that the growth with respect to dimension is going to be much reduced in this estimate. Okay. But it's the same kind of characteristic. We have a convergent term here plus a term that's order epsilon. Okay, so that's going to be the best accuracy we achieve. I should point out here that we need no strong condition on omega in order to get this. So this is a very nice thing. If you have a function f that's smooth over the whole extended domain D, you actually don't need to assume really anything about omega at all in order to get an approximation rate.
Can I ask?
Yes.
I'm confused now because for your interpolant you want L2 on omega, but then as long as I was following, f was the function that actually is not defined in D, and now you're putting like regularities on the f on D.
Yes. So in order to get this error bound, we need to assume that irregularity of f on D. And the reason for this is if we look back to this best approximation term, we have this polynomial p that we're going to pick to get us a certain rate, but then we have to know how large p is growing on D. And that is essentially, that requires us to be able to say in this first setting here, it basically what we have to do is say, well, how smoothly can I extend f to the whole of D? Okay, so that's this case. You use a Sobolev extension argument, and then in this case, you just assume f is smooth over the whole of D. So you've already got that extension. So, yeah. Are there any other questions?
Just because I see, maybe I missed the point, but I see the root of all evil is the fact that you were regularizing your interpolants in omega.
Yep.
And now you're saying, well, we're going to regularize, and effectively it seems to me that you could have released that and asked regularity on the whole D for your interpolant.
Yes, so I fully agree with you, but this is the limit of what I can prove at the moment. And actually the main reason I'm assuming regularity on D here is so I can use the mixed Sobolev spaces. If you know how to define mixed Sobolev spaces on omega, on an irregular domain, and then you know a Sobolev extension theorem that scales nicely with dimension, then you could do this on omega as well. But I have no idea how to do that, and I've asked plenty of people and no one else seems to know either. So here we just hit this by assuming regularity over the whole of D. Okay, let me skip this because I'm running quite short on time. Let's talk about sample complexity. Okay, how many samples do we need in order to get a stable approximation? So if we go back to this main theorem here, this relates to bounding this constant here. If we bound this constant, we can make it close to 1 or 2 or whatever, then we get a quasi-optimal approximation here up to this stable approximation term, and we also get good conditioning of the mapping. So, how do we do this? Well, it turns out we can actually take techniques from tensor product domains and extend them to irregular domains with a few tricks. And so the key driver, exactly as we saw in tensor product domains, is going to be this Nikolsky inequality. Okay? But now the domain in our Nikolsky inequality is omega, rather than a tensor product domain. Okay? So what you can show is the following. The number of measurements you need, m, should scale like the Nikolsky constant squared times by log factors, and that's sufficient to ensure boundedness of this constant. And this comes by fairly standard matrix Chernoff type bounds for random matrices. So, the question, exactly as in tensor product domains, the question then becomes an approximation theory one. How large is Nikolsky's inequality for a given polynomial space p lambda and a given domain omega? And again, this is another point where I have to admit that I don't know very much about this, and actually I believe that there isn't very much known about this, because we looked around in the literature for a long time and couldn't really find any results in this direction. However, we can say a few things about certain domains, and quite a large class of domains as well. So suppose if we want to say something about this constant, one way in which we can approach this is to try and think up our domain omega as a union of rectangles, because we know the Nikolsky constant on a rectangle. Okay? And so that's kind of what we do here with this property. I'm going to say omega, my domain omega has what I call the lambda rectangle property if it's a union of hyperrectangles of volume at least lambda times by the volume of omega. Okay? So I can consider any domain that's a union of hyperrectangles, but I can't allow those hyperrectangles to get too small in volume. Then in that case, you can prove that the Nikolsky constant squared behaves like n squared divided by lambda. So of course, it's perhaps not surprising that you pay a factor of lambda here through the analytical technique that we're using. Okay. So this holds for any lower set, and the key point here is we get a bound, again, that is independent of dimension, just modulo, as long as lambda doesn't depend on dimension in some way, some domain. And this is exactly the same up to lambda as the behavior of this Nikolsky constant for tensor product domains. So for any irregular domain that has this lambda rectangle property, we need the same asymptotic sample complexity when sampling from the uniform measure as we would do when approximating a function on a tensor product domain with from the samples drawn from the uniform measure. So we can extend this to very general classes of domains. Just to point out, here are some domains that have the lambda rectangle property. Of course, an L-shaped domain is a union of two rectangles. This is a union of countably many rectangles of size lambda being about a half. And also this is a union of countably many rectangles as well. So these domains I think are quite interesting because you can think of scenarios where this represents some linear dependence on your parameters that you didn't know in advance, and this represents some condition that your parameters, y1 squared plus y2 squared can't be too small. Okay, so you can imagine these scenarios occurring in certain applications. I should point out though that this is a limited result. You can easily construct domains that don't have this property. A triangle does not have the lambda rectangle property, nor does a circle. So there are some very simple domains for which we cannot bound the Nikolsky constant. So if you have any idea how to do this, I'd be very interested to hear them. I think many of these things, many of these constants are completely open questions in 2 or more dimensions. Okay, so just to finish up, but let me show a few numerical examples. So first of all, let me just start with a 2D example, just to point out that this really does work. Here are 2 functions of 2 variables. You can see their domains here. On the function on the left, this is obviously a Lipschitz domain, and we have a function f that's singular at 0. So it's singular on D, but smooth on omega. And we can approximate it to 10 degrees, roughly 10 digits of accuracy. Here we have obviously a domain that's not Lipschitz. but the function f is now smooth over the whole of the bounding box. So again, our theoretical results on the best approximation rate say that we can approximate this to high accuracy using with a certain rate. Okay, so this is sort of the two-dimensional case. Let's go to higher dimensions. So one thing I wanted to illustrate with these sample complexity estimates. So to illustrate that, let's set up a problem. So here's a function f, and it's defined over an annulus. Okay, the outer radius is r, the inner radius is r over 4, where r is a number between 0 and 1 that we're going to vary. And we're going to approximate this in various different dimensions. And what I'm going to do, so we know that from the results that I stated, that we know that the sample complexity should be n squared times log n. Okay, so it should be quadratic in n. And I'm actually going to break that to make things interesting. I'm actually just going to do log linear sampling. And then look at my approximation. Okay? So this is the approximation error versus n here. Okay? And so this is the error on the y-axis. And each curve is a different dimension. And what you see is you see instability. Okay? You see the fact that this amount of oversampling is clearly not enough to have a stable approximation. These are blowing up. Okay, obviously when you go to higher dimensions, you're not seeing this growth, but that's because I'm using a hyperbolic cross index set throughout. So in higher dimensions, I can't use a hyperbolic cross index set of big enough degree to see the real blow up. Now let's change R. So here R is 1. Now R is 3/4. Okay, so all I did is just change the domain here. And now everything seems to be converging. Okay? If we change R again, change R to a half, things seem to be converging with this n log n oversampling. And you can do a bunch of experiments. You can actually compute this constant that we need to compute to estimate the sample complexity. And what the resulting conjecture that we have is that actually, even though our theoretical result says that we need to quadratically sample, actually we only need to sample in a log linear way whenever omega is compactly contained in D. So informally, if there's some gap between the boundary of D and the boundary of omega, log linear sample complexity should suffice. And the key point I want to make here is this completely comes from your SVD regularization. It completely comes from the fact that you are throwing out polynomials that behave badly on D and just retaining the ones that behave nicely. Okay? And that seems to be driving this lower sample complexity. And this is a conjecture, it's an open problem. Just a couple final experiments. So we can change the polynomials we use. We can use Chebyshev polynomials. And again, you get provable approximation rates in various different dimensions. We can analyze this case as well, and I won't go into it. And we can also use non-polynomial things. So we can use a cosine basis. Okay? There's really not that much in this talk that's specific to using polynomials per se. Of course, if you're going to use something like a cosine basis or a Fourier basis, you need your domain omega to be compactly contained in D, because otherwise you won't be able to match these sort of periodicity conditions that you need. Okay, so let me just quickly conclude. So multivariate polynomial approximation in tensor product domains is increasingly well understood. We have a lot of results. We know how to compute them. There's a lot of theory supporting this. What I've tried to do in this work is present a first analysis of a big sort of question about polynomial approximation in irregular domains. As I've alluded to in the talk, there are lots of open problems, many things I don't know how to solve, some of which we've already mentioned. So there are many sort of interesting questions to try and look at. So for example, there are questions about regularity theory. What are good regularity conditions? How can you define things like mixed spaces on irregular domains? Questions about efficiency, Nikolsky inequalities for irregular domains in arbitrary many dimensions. These things seem completely open. Practical questions about efficiency. How do you design better sampling points, as has already been discussed in a few talks? How do you do adaptive sampling, optimal sampling maybe, or quasi-optimal sampling, et cetera, et cetera. In practice, how do you avoid doing a singular value decomposition? That's pretty expensive. In low dimensions, actually, we know how to do this. We can use techniques from randomized numerical linear algebra to avoid an explicit and costly SVD. And then on the algorithm side, okay, I don't really want to do least squares. I'm a compressed sensing person, but I do not know how to do compressed sensing yet with this problem because of the potential for ill conditioning. Final thing I want to say, this is part of a larger program, depending on whether you're in Europe or North America, on numerical approximation using frames rather than bases. And this is something that can be useful in a variety of contexts. Really what I've presented is one instance where you end up with a frame in numerical approximation. Okay, so that's it, and thank you. Yes?
Questions?
So why don't you just orthogonalize on the region omega directly using, I don't know, Gillespie factorization or something? Why do you have to embed it in this bigger domain? It's a provocative question.
Well, so to orthogonalize, you have to start with a basis, right? So embedding it in a bigger domain is a way of us defining an orthogonal basis, right?
No, you can just get orthogonal polynomials with respect to the measure on the
right, but you have to
on the region.
You have to start with you start with a basis that you then orthogonalize, right? So if you're going to construct an orthogonal basis, you need to start with a basis, right? And then run Gram-Schmidt or something more stable.
Start with an ordering of monomials and then go up.
Right, but so orthogonalizing starting from the monomials is not numerically going to be a very good idea. Okay? And I think the more important point is if I want to orthogonalize a basis, I have to compute inner products over my domain. So there's a question about how I do that. And then there's a question about I actually need to know the domain in order to orthogonalize because I would have to compute inner products over it. And what I'm essentially saying in this talk is you actually don't need to do any of that. That's an additional computational headache that you actually don't need to do. You can work directly with your orthogonal basis on the bounding domain, and actually things, as long as you regularize in the right way, things will be perfectly fine. Yep.
So you didn't talk about interpolation, but
Yep.
I was just wondering, there's this work of Narayan and Xu on the least orthogonal interpolant.
Yep.
Yeah, do you have any comparison or ideas how it... okay, it's two different worlds, but still.
So is that on tensor domains or is it on irregular domains?
Irregular domains.
I don't know this work, although Akhil is a collaborator, so perhaps I should do. We didn't spend very much time looking at interpolation because I think it's a very interesting question. I simply don't really have a good idea how to do interpolation, how to come up with good interpolation nodes on an irregular domain yet. But so if you know of something that you think might be useful, that would be great.
Can you just do Tikhonov regularization to avoid the SVD part?
Yeah, actually, so it's a very good point. So you can do Tikhonov, and not very much changes in terms of the analysis. Why do we choose to do SVD? I think it makes things a little bit more apparent from the analysis perspective, what's happening. But yeah, you can do Tikhonov, and it doesn't change very much. But yeah, so we chose to do SVD because it's... well, actually, there are two reasons. So first of all, it makes the analysis a little bit more apparent, a little bit more clear what's going on. On the practical side, so my collaborator, Daan Huybrechs, he's actually doing this in 2 or 3 dimensions and using it to solve PDEs on irregular domains. He has a fast algorithm for computing these approximations, and it is based on a SVD. So it is based on essentially doing a fast SVD computation. Okay. So it's not clear that you could do that via Tikhonov.
Oh yeah, go ahead.
So I'm interested in maybe iterating on the question I make always, but since now you need to regularize, right?
Yeah.
Because of the condition you put it wrong. What's the link between the regularization you choose and some kind of optimality? So on the best basis you can choose on your omega domain.
So okay, so that's a good question. So if let's go back to my main best approximation bound. So here's my best approximation error. So if epsilon is 0, if I don't regularize, I just have the inf. I have the best approximation in the uniform norm. That's great. Problem is I cannot compute that because eventually I'll have the ill conditioning. I have to deal with the ill conditioning. If you just run this in backslash, you will see. I mean, you can just use backslash because backslash will do some kind of regularization on a ill-conditioned problem. You will see actually convergence plots that look very similar. So you, just to point out, this is the slide that I skipped. This is a 1D example where we vary the epsilon in our SVD threshold, and you see it converges nicely down to epsilon. In fact, a little bit better than epsilon in this case. If you just did backslash, you'd see something very similar to this because it's doing some kind of regularization as well. So if you want to, if you want to analyze, say, if you backslash is your algorithm and you want to analyze what that's doing, you will end up still having to say something about this kind of quantity because it's doing some inherent regularization anyway. So. Yeah. Can I go on? I'll just say one other point. There is a fundamental issue here, is that the polynomial that gives you the best approximation, so the inf here, its coefficients can grow exponentially large in n. So they can very easily overflow. So they're not computable for large n. Okay, so there is an inherent problem in that case.
Yeah, with that note, I think we'll thank Ben one more time.